because you're gonna see.
I have good news. Chapter 10 is easy. Extremely easy. It's so easy, I don't even know how much you're gonna need me past today. Today you need me because I have to teach you like one new thing, but then I almost feel like you guys could do the whole rest of the chapter on your own. And the reason is because it's just the same stuff over again, but with memes instead of proportions. You already know it all. It all already happened. But I do need to teach you one thing today, and that's pretty much it. Isn't that wonderful? So you have deep breath, smooth sailing here. There's no type 1, type 2 errors in this chapter. There's no power. There's no alpha level. There's none of that conceptual stuff. It's very, very like, let's follow the steps, which we like. I like, I should say. Okay, but today I do need to teach you one thing, before we go to all of that very easy calculation stuff. What I want you to do before I start is grab your yellow sheet. You're gonna use your yellow sheet today. And I'm trying to draw on your ability to use your own common sense. So pretend I wasn't here, like there's no lady. No, oh no, I have to teach myself, which happens a lot in college classes. The lady is there, but not approachable. So, just how could you figure this out on your own? This is something you could figure out on your own, minus one thing. Okay, so let's talk about the title of this chapter. The title of this chapter is Confidence Interval. It's not the title, sorry. The Mrs. Talbot title for this chapter is Confidence Intervals for Mean. Okay, can you guys look on the front side of your formula sheet and find the thing that talks about confidence intervals? And I was talking to a student about this, and I really like how the book goes back, and you might not like this. This is a 50-year-old lady like, and maybe not a teenager like. I like how this book goes back and forth between confidence levels and hypothesis tests. You might hate that. So that might feel awkward for you, but what that says to my brain, being a math major and being an old lady, says, oh, if I put it in their brain once, it's gonna be there for a while. If I can come back to it and put it in their brain again a month later, like then we're getting somewhere. Like that's something you'll actually remember. But I'm hoping that's what the book was thinking when they structured it this way. They're like, okay, let's do confidence intervals, let's do hypothesis tests, let's go back to confidence intervals, back to hypothesis tests, and then you're like, oh, okay, I can do it. I can do these for anything. That's kind of what I was thinking. Okay, so what does it say under confidence intervals? Statistic plus or minus critical value times standard error. Okay, let's break down what we have here in terms of mean. So I want to go very slow. Statistic, when you're talking about a mean, is the sample mean. So statistic means sample, right? Everybody good with that? We were struggling with that in chapter 7. We're not struggling with that anymore. So statistic means sample. And when you're talking about a mean, this is the symbol for sample mean, which is X bar. Okay. Everybody good with that? Okay. Plus or minus critical value with D star. D star is how many standard deviations out on either side. And D star is the thing in question today. So just hold that. That's my foreshadowing. Okay, now I want you guys to flip to the back of the page. And notice that this says standard error of statistic. And you're looking in the standard error column, and I'm pretty sure you're not finding this. Look down the standard error column. You can sort of see where it's supposed to be. You're in the one sample mean section for X bar. But what is there instead? S of X, yeah, S of X, which is the sample standard deviation. Okay, so here's what I'm saying. This is what we would like to calculate. This is what we would love to do. I would like to be able to plug in the sample mean. I'd love to be able to use critical value Z star. I would love to be able to plug in standard deviation there. But as I said, if you don't have the population mean, how likely are you to have the population standard deviation? You're not gonna have it. Okay, so thinking about all the squishmallows in the world, if you don't know the average size of all the squishmallows in the world, are you gonna know how much that varies from the mean? No, you don't know it. It's an unknown value because it's population. And the whole population of squishmallows everywhere is just too many for us to calculate. We're too lazy. So the problem is we're not gonna have this. If we don't have the mean, are we likely to have sigma? What do we use to estimate sigma? Okay, so look at that column I was telling you guys to look at. What did they replace sigma with? S sub X. Okay. And it's very simple, like when you're thinking about it, but it's important to make the note. Okay, what do we use to estimate sigma? S sub X equals the sample standard deviation. Okay, now I'm gonna let you set up that part. You're like, you just had that whole talk for us to write one little tiny thing in the yes, yes, yes. Lexi, will you tell me when you're past the first formula here? Just to, will you tell me when you're here? You're okay. I just wanted to scooch it right there. So I've been setting this up. I'm curious, did any of you guys notice in your calculator or in any of the books you're reading or any of the videos that you watched anything about the T distribution? Have you heard of it? Did you notice that there's TCDF and inverse T in your calculator? You can it's right underneath normal CDF and inverse norm. There's actually a lot of different distributions in there. We're only gonna work with T pretty much. And I'm going to draw a curve in this spot right here in 3 different colors. So if you guys want to grab your baskets or grab colors out of your bag. I'm gonna use blue, pink, and green, I think. Like this, and this. Do you have to do the same thing? No, of course not. Is it okay if I scooch it right here? Okay. So if we take out sigma and replace it with S sub x, which we have no choice. You're not going to have sigma. That would be a really special problem if you did. It would be a very contrived stats problem from a book where they would give you sigma for some reason. And then you got to think to yourself, if I know stuff about the population, why would I ever do a confidence interval? Because I would be 100% confident if I had all of the information about the population. But whatever. You know how textbooks are, they contrive things to make you do stuff. But the capture rate will be much lower than our confidence level. It won't match. So we need it to match. That means we need a larger critical value. So we need to talk about a new curve. And we're going to use this curve anytime that we're working with means. Okay. The first thing I want you to do is your best attempt. Okay, so go to 0, count up 1, 2, 3, 4, 5, 6 boxes. And then go down 3 over 2 on each side. And then go down 2 over 2 on each side. I'm doing this in my original color. Okay, so that's just the normal curve. I want to put the normal curve there for reference because we're working with something that's different from the normal curve. So we need to figure out what makes it different. And I need to introduce to you a new concept called degrees of freedom. If you're from bio, don't give me that face. Okay, let me explain to you what degrees of freedom means. And so this is important for our understanding of the t-distribution. The t-distribution is different because there's infinite t-distributions. There's only one standard normal curve. There he is, right there. There's infinite t-distributions. Okay, I have come up with a very sophisticated problem here for you to describe what degrees of freedom is. This is my post-it note of lines. Okay. Ivan, give me an easy number. 3. Okay. Hold on. I did this wrong. I have to give you a total. Okay. Okay. Now, Jeremy, give me another easy number. Great. I'm loving how your brain is working. Okay. And let's see. John, give me another easy number. 2. You guys are my favorite. Okay. You didn't make me do anything difficult. Okay. Now, if I say I have 4 numbers and I know that they add to 100, Were we free to pick this number? Yes. Were we free to pick this number? Yes. Were we free to pick this number? Yes. Are we free to pick this number? No. So when you have 4 observations, the degrees of freedom is 3. 3 of them are free to choose. The last one is set because you're adding up to a very specific total. Okay. Now, for us, our degrees of freedom is n minus 1. So total number of observations, sample size minus 1. Minus 1 because you're not free to pick that last one. Okay, which means there's technically infinite t-distribution curves depending on the degrees of freedom. We're just going to draw 2 of them because we only have time for that. But you'll get the idea. Okay, so I want you to go up to 1, 2, 3, 4, 5 dots up in your different color. I'm going to do pink. Go down 3 over 2 on either side. And then go down 1 over 3 on either side. This would represent a curve that's about degrees of freedom of 20. Meaning what was the sample size? 21. Okay, now come down like a box and a half. And this really shouldn't go flat, but and when I looked, this is about degrees of freedom 4. Okay. The conclusion that we're going to make here is that as degrees of freedom increase, your t-distribution curve will approach standard normal. Okay, why does that make sense for every single lesson I've ever taught you in this class? Every single lesson. What's the thing? What's the thing that affects every single thing? Increasing sample size. Yeah, I know. They're gonna put it on my tombstone. She was really hoping to increase sample size. That's what it's gonna say. Your lies is tough. Sample size. Uh, so there will be a point where the sample, if you do a survey or something, the sample size is so good, so high, you could just use the standard on the curve if you wanted to. And people will, they'll use it illegally. we know how to do it properly, so we won't use it illegally, but you could. When your sample size got so high, you'll notice that when you're doing T-star, which is what I'm gonna teach you next, they're gonna come out to be equal to T-star. Do you need to worry about that as a conceptual thing? Not really, because you're just gonna go on the calculator and get a number. But it might be cool for you to think, oh, if I do T-star for a really high sample size, it came out to be 1.96. That's interesting. It came out to be exactly the same thing as T-star. Why is that? Oh, that's because the sample size was so high in this particular thing, which is a good thing. So really, this is, I think on the team test, I asked you to sort of sketch this out. But for the most part, you're just going to go straight to the calculations. Did my degrees of freedom thing make sense? Okay. Would you be excited to know that we're almost done already? I know. I need to teach you how to do T-star on the calculator and talk about the conditions, and then we're done. So grab your calculator and do not just watch me. You should make yourself do this. Self-discipline. Okay, everybody. So the first thing I want you guys to do before I forget, you guys know about my little short-term memory problems. I want you to come here. And you don't need to erase that. You can leave it. I just want mine to be spaced properly. Okay, above the critical value, just make sure that you have Z star or T star. It could be either one. If you're working with proportions, chapter 8, it's Z star. If you're working with means, chapter 10, it's T star. They don't get mixed up too many times. So like your whole chapter test is going to be using T star, so you'll be fine. Okay, now flip to the back. So this is going to be your one sample standard error, and this is going to be your two sample standard error. Exactly what you would expect. Like I said, you guys could almost teach yourselves this whole unit because if you know how to put the pieces in the spots, you just look on the sheet to find the piece that goes in the spot. So like I said, I need to teach you T-star and then it's smooth sailing from there. Just great. Okay. So just make sure you've got that, then scooch that off to the side. Okay. Calculating the critical value of T-star. T-star equals inverse T. I think it's capitalized in the calculator. Yeah. Inverse T is the fourth one down, right past inverse norm. Okay, do you guys remember what we would type in to find Z star? Is it in your brain anywhere? Is it in there? 1 minus percent confidence divide by 2. And then for proportions, we would put 0, 1, remember? But for us in this problem instead, we're going to put degrees of freedom because that's what determines how close to the standard normal curve you're going to be. Okay, couple of notes. T star is an absolute value. Do you guys remember that Z star was also an absolute value? So it's always positive. Even if you get a negative number, you just ignore it, make it positive. And we use T star for means, which is chapter 10, and Z star for proportions, which was chapter 8. Okay, I'm going to do A with you, and then I want you guys to do B on your own. T star equals inverse T 1 minus 0.95 divided by 2, comma. Okay, and if the sample size is 12, what's the degrees of freedom? 11. Man, that's the math we're doing today. Yeah, we like it. Okay, so let's type it in. And remember about the parentheses. Inverse T 1 minus 0.95 divided by 2. Remember where the parentheses go around the top because of order of operations. It's the fourth one down in it's right after inverse norm. Degrees of freedom 11. Okay, and because we're just reminding ourselves how this works, I'm going to write down the absolute value of negative 2.2 equals 2.2, but I would never do that on an actual paper. I would just write 2.2. Does that make sense? Okay, also on your test, you don't have to show any of this. You need this is required here. Okay, you guys try B for me. 48 random observations is the sample size, by the way. It was me trying to be fancy. Do you see my fanciness there? Yes. Does it? Let me come over there. I'll pay a house call. Let me just figure out. Did you guys get 1.68 per chance? Okay. Okay, I'm coming. That's what they would do, they would like, well, definitely, yeah, okay. Yeah. I just think that you should probably use one of mine while you're here, and then when you're at home, literally just Google university calculator online, just gotta do one, right? Yeah. Because that's for the website. I'm not stressed about it. We have a lot of them. It's okay. I'll see if I can find one when we're done. Okay, any questions about this other than that missing inverse T? You guys got 1.68? You good? Okay, we have one more thing to discuss and then I'm done. What, did you find something?
No.
Oh, okay. The reason that it's not on your calculator is because they give you, when you take the AP test, they give you like printed out tables with all the like normal CDFs on them. And you're supposed to use like the paper table to go back and find it, but I don't think that's necessary for us. But when I first started teaching this class, we used the paper tables for everything. And then now it's like, I don't even know what they look like anymore. It's funny how things change. Anyway, okay. So let's talk about the conditions. This is the last thing for today. You still need the random condition. It's exactly the same thing as you would expect. So just gonna make a little note there that you should state that they're separate samples if they are two sample situation. That's just me trying to remind you that that's a thing. Okay, now the 10% condition, there's two options. Neither of them are new to you. So if you have random sampling, you say n equals blank is less than 10% of all blank. Or if it's an experiment with random assignment, 10% does not apply. And you can just skip it, but that should not be news to you. That's the same dealio. Chapter 8, chapter 9, same thing. Okay, so have we had anything new yet? Anything unexpected? Okay, so this is the last thing. What do we do for large counts? N times P is greater than or equal to 10. N times 1 minus P is greater than or equal to 10. Is there a P in any of these problems? No. So you're like, cripes. What did we do when we didn't have P? Does anybody remember? Yes, it's called the central limit theorem. Okay, so n is greater than or equal to 30. So CLT applies. Okay, now This is new for chapter 10. If n is less than 30. And this is going to be an annoying part of this chapter, but it's easy. If n is less than 30, then you have to check for normality with a dot plot or box plot. So you have to make sure that you don't have a really huge skew situation. And that's it. Do I have a joke is the question. What chapter is this again? 10? Oh, I like this one. It says, maybe it'll come up there. Maybe today. Maybe at some point today. Maybe soon. Maybe. It says, the larger the sample size n, the more confident you can be that your sample mean is a good representation of the population mean. In other words, the n justifies the mean. Is it gonna, there we go. Yes. What? Oh, I didn't do it yet. I will.
Yeah.
It looks like, guys, I Googled, if you could look at the screen for a second. I Googled, inverse T calculator and a bunch of stuff comes up for your homework. There's a bunch of them. This one is, you just put the degrees of freedom in, click the confidence level. Let's check it. What was the last one? 47 degrees of freedom and that's wrong. Oh, there we go. 1.68. Does that make sense? You guys find it? You good? Do you see what I did? Okay, just want to check. Okay.